Digamma comes to your rescue. This is a problem by Gofani Sade, and credit to him for the problem. And we are gonna solve this. And while solving, we'll see that how digamma actually makes this problem simpler. And because we already know a lot of properties of digamma, and that becomes helpful. So let's see how we proceed with this problem. And also over here, this symbol, this denotes the floor function, right? And by floor function, what I mean is, so let's say if I have floor of 2.5, that becomes 2. Floor of 2.9, that also becomes 2. So it basically rounds down to the nearest integer, right? Okay, so let's see. And usually, what we do is, whenever there's a floor function, we try to break integrals in terms of like multiple integrals. Okay, so what I'm saying is, let's say if we have integral from 0 to infinity, a floor of x dx, right? So now what we can do is integral from 0 to 1, and then in this range the floor will just be 0, right? Because no matter, let's say if it's 0.5, floor of 0.5 is 0, right? So again, from 1 to 2, floor of x will just be 1, and from like 2 to 3, floor of 2.5, let's say in this range the floor of x will just be 2. So you see, so this is the trick we apply. So but here as well, so what we do is, we write this integral as sum from n equals to 0 to infinity of integrals from n to n plus 1, right? And when x is between n to n plus 1, I can actually write this as just n, right? Because in between, like n to n plus 1, the floor is always n square plus x plus 1 square. So yeah, so over here what I'm doing is basically I'm writing the single integral in terms of the multiple integrals, and like I'm just breaking the integrals part by part. So this is basically from 0 to 1 plus 1 to 2 plus 2 to 3 and so on, and that's basically 0 to infinity, right? So yeah, this is a really good idea which is helpful if you have floor functions. Now after this, let me just integrate it. Sum from n equals 0 to infinity, and now this is from n to n plus 1 dx by x plus n square plus 1 whole square, right? So this is just like x square, and sorry, 1 over x square. So its integral will just be x plus n square plus 1 to the power minus 1 by minus 1 from n to n plus 1, right? Now if we evaluate this, we get 1 by n square plus n plus 1 minus 1 by n square plus n plus 2, right? We can evaluate that like yourself, it's not too hard, right? Now how do we proceed ahead? So for such infinite sums, like this actually converges, and like how you actually find the answer is, like, you might have other ideas, but using digamma is also a really good way, because there's actually a formula, like, like the digamma function of okay, let me just get this formula over here, of n plus 1 is negative of Euler Masoni constant plus nth harmonic number, right? So we can actually break these as like a fraction in n plus a, fraction in n plus b, something like that, right? And then we can invoke this identity. So let's see how we actually do it. I'll just go step by step, and in the process, maybe you will be more clarified towards it. Okay, so first of all, there's a property that sum from n equals to 0 to infinity of 1 by n plus p n plus q. This is actually equals to digamma of p minus digamma of q by p minus q. And we can also break these n square plus n plus 1 in this form, right? And then we can invoke this like formula. Also, let's prove this formula just in case if you are unfamiliar. And the benefit of getting in this formula is, after we have this answer in this way form, we can then use properties of digamma, like let's say, or maybe reflection formula, or let's duplication formula, and then get the answer. First of all, let's prove this formula. and then we will get back to our original problem, right? So yeah, let me mark over here because this is our solution, and now we are trying to derive formula. So how we do is, first of all, we can break it into partial fractions. So this becomes 1 by, I can write p minus q, and then I can have it as n plus p minus n plus q by n plus p n plus q, right? Now this becomes 1 by p minus q, so n from n equals to 0 to infinity, 1 by n plus q minus 1 by n plus p, right? And now I can again write this as sum from n equals to 0, let's say from 1 to infinity of 1 by n plus q minus 1 by n plus p minus 1, right? Again, over here, you might know that the sum representation for the nth harmonic number is basically a sum from k equals to 1 to infinity of 1 by k minus 1 by k plus n, right? So you can reduce this sum to a familiar like expression, which is sum from n equals to 1 to infinity. I can now write this as 1 by n minus 1 by n plus p minus 1 minus 1 by n minus 1 by n plus q minus 1, right? So note that these two expressions are actually equivalent because 1 by n cancels out, right? And so now the first expression will just become William-Masoni constant plus gamma function of n plus p minus this becomes William-Masoni constant plus gamma digamma function, sorry, not gamma, digamma function of n plus q. So we see that the formula is proved. It's digamma of n plus p minus digamma of n plus q by p minus q, right? Okay, so now that we have this formula, we can now use that formula. But before we use that formula, we need to factorize the expression. So if we factorize it, this will be sum from n equals to 0 to infinity of 1 over n square plus n plus this will be 1/4 plus 3/4 minus we will have n square plus n plus again 1/4 plus 7/4, right? And so that gives us okay, so we will have sum from n equals to 0 to infinity. This is n plus half square plus root 3 by 2 square minus this is n plus half square plus root 7 by 2 square. Now you can use the sum of squares formula. That gives us sum from n equals to 0 to infinity 1 over n plus half plus I root 3 over 2, and then n plus half minus I root 3 over 2, right? Minus we have n plus half plus I root 7 over 2, n plus half minus I root 7 over 2, right? I just use the sum of like squares formula and also the fact that I square is -1. Now after this we can use the formula we derived earlier. We know that okay, over here, I'm sorry, I made a little bit of mistake. Over here, this is actually just digamma of n, right? So over here, this n is same as k. So this would actually just be digamma of p, digamma of q, digamma of q, digamma of p. Okay, I'm sorry for that mistake. Yeah. Okay, so now we know that this is gonna become digamma of p, half plus I root 3 over 2 minus digamma of q, half minus I root 3 over 2 by half plus I root 3 over 2 minus half minus I root 3 over 2 will just be I root 3. Similarly over here, this is digamma of half plus I root 7 over 2 minus digamma of half minus I root 7 over 2 by I root 7, right? Now notice that these two half plus I root 3 over 2 and the half minus I root 3 over 2 actually sum up to 1, right? And same is the case over here. So that means if let's say this is some number n, this is just 1 minus n, right? And we already have formula for that. We have formula that digamma of 1 minus n minus digamma of n is actually pi by 10 and pi, right? And how do you get this formula? You get this formula from the reflection formula of gamma function, right? We know this is pi by sine n pi. Now, if you take the log n and differentiate, you will have minus digamma 1 minus n. That correct? Minus, okay, if you take log and then differentiate, yeah. And then you will have plus digamma of n, and this will be minus pi and then log sine n pi, which is cot n pi. Okay, yeah, cot. Okay, so you have pi plus log of sine n pi, and if you differentiate log of sine n pi with respect to n, you will have 1 by cos n pi, sorry, 1 by sine n pi, and then cos n pi, and then also a pi, right? Yeah. Okay, so because of which there's a pi over here. Actually, I shouldn't really have skipped these steps over here. Let me show you. So basically, this is, let me first take the log, right? And then this becomes, okay, log, I'm sorry. This is getting messier now. Okay, wait, let me go slow actually. Log of pi minus log of sine of n pi, right? Okay, so this one becomes negative digamma 1 minus n, this one becomes digamma of n. If I differentiate with respect to n, and this becomes 0, and then minus, this becomes 1 by sine n pi cos n pi times pi, right? Now if I multiply both sides by negative 1, this becomes digamma of 1 minus n minus digamma of n is equals to pi by tan and pi, just as expected. Now you can use this formula because over here we realized that if this is n, this is just 1 minus n, right? So if you use the reflection formula, what we get is 1 by I root 3 times pi by tan of pi times half minus I root 3 by 2, right? Over here, minus 1 by I root 7, this is pi by tan of pi times half minus I root 7 over 2, right? And now that gives us 1 by I root 3 pi. So this is tan of pi by 2 minus something. So we know that becomes cot. But again, if I take reciprocal of cot, that again becomes tan, right? So this becomes tan of just pi I root 3 over 2, right? Minus 1 by I root 7 pi times tan of pi I root 7 over 2. Now I know that tan of I theta is just I times tan s of theta. So that this becomes I pi tan s of I root 3 over 2 by root 3 minus again I pi tan s of, okay, I forgot pi over here. Okay, okay, actually I should have removed I and then written pi. Yeah. And then this becomes pi root 7 over 2 by I root 7. Now I cancels out. Also I cancels out. And so this now becomes pi by root 3 tan as pi root 3 over 2 minus pi by root 7 tan as pi root 7 over 2. I know I actually made a lot of mistakes over here while solving, right? But this is the answer. Pi by root 3 tan as pi root 3 over 2 minus pi by root 7 tan as pi root 7 over 2. Yeah, I made a lot of blunders, but yeah, that's fine. You got you just heard solution now. Summarize, we first use the technique for the floor function, and then we use the digamma function, like how we can break this kind of fraction into a digamma function. And then after that, we use digamma function, and then we revoke the reflection formula. Also, there are some definitely there are some restrictions, right? So this formula only works if n is not an integer, right? Again, this formula only works if p is not equals to q and pq are not negative integers. So there are some restrictions which I did not write, but yeah, we need to be careful about that too. And yeah, so that was the solution. That's how you can solve this problem. Definitely there are other ways too, right? Because like you can definitely simplify this in other ways as well. This isn't too complicated, right? So yeah, I think hope you got the idea, and that was the solution. Hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the upcoming videos too.